as you've heard from Paul, in July of last year, CERN, big particle physics laboratory outside Geneva in Switzerland, announced the discovery of a new particle, which we think may be the Higgs boson. And I want to convince you that this was indeed a massive discovery. Massive in the sense that, as you can see on the screen here, the facility required to produce this new particle is very large. This is the airport of Geneva, runway about 5 kilometers long. The circumference here is 27 kilometers, and the experiments that produced what we think is the Higgs boson were conducted about 100 meters underground around this big ring here. So to set this in context, I would like to tell you a little bit about the story of the universe so far. So what you see here is an image of the expansion of the universe as observed, for example, by a satellite telescope, which sees stars, galaxies, and so on, and looks back towards the beginning of the universe. The beginning of the universe occurred something like 13.7 billion years ago. And what we physicists try to understand is how the universe got from that beginning to where we are today. Now you may say, well, let's look through telescopes. But those telescopes cannot look all the way back to the beginning. There's a sort of cosmic firewall, a plasma that filled the very early universe that telescopes can't see through. And the way to see through them is by studying the elementary particles of matter. So this situates for you the evolution of the universe from the very beginning to where we are now. So over on the right-hand side here, we see the size of the universe today, about 10 to the 28 centimeters. 10 to the 28 is a very big number. You can visualize it as being the American budget deficit expressed in cents and squared. And then you get something like 10 to the 28. The other end of the scale here, we have the smallest distance that we physicists think that we can reasonably speculate about, something of the order of 10 to the minus 32 centimeters. And roughly speaking, in the middle, we have the human scale. This is a picture of Albert Einstein and his kid sister. So what goes on inside Albert Einstein and his kid sister? So we know they're made of molecules. Molecules are made of atoms. Atoms contain nuclei with electrons orbiting around them. What we're trying to do now with our experiments at CERN that I described to you earlier on is to probe back inside those protons, inside the quarks, inside the protons, back as far as we can towards the beginning of the Big Bang. So as I said, telescopes, they can see stars, they can see galaxies, but if you really want to understand what was going on at the very beginning of the universe, you need a sort of super microscope, and that is what our facility, the Large Hadron Collider, LHC, enables us to see the physical laws that held in the first fractions of a second after the Big Bang. So many of the advances in this field were actually made not in particle physics laboratories, but by observing cosmic rays coming from outer space. As you may know, the Earth is bombarded all the time by energetic particles which rain down from the cosmos. When they hit the upper atmosphere, their energy is converted into the masses and energies of other particles. And in the first half of the 20th century, many of the fundamental discoveries in particle physics were made by studying the debris from these collisions. But around the middle of the last century, it was realized that if you wanted to understand these things in detail, if you wanted to study them systematically, then you would need to reproduce those cosmic ray collisions in the laboratory, and that's how big particle physics laboratories, such as CERN, such as the Large Hadron Collider, were born. Now, as has already been described to you, the work with these particle accelerators during the second half of the 20th century has established something that we call the standard model of particle physics. Here you see Abdus Salam, one of the inventors of this theory, who came originally from Pakistan. That was in the 1960s. In the 1970s, experiments began to confirm these ideas, in particular experiments at CERN. Here you see some people in some typical 1970s lab coats. You don't see many of those anymore. Those were followed up by more detailed experiments, both at CERN near Geneva and at other particle physics laboratories around the world, confirming predictions of the theory at the level of a fraction of a percent. So what does this so-called standard model contain? So on the one hand, it contains the fundamental particles of matter, what make you up. So inside your nuclei, there are things called quarks. We know that there are 6 different types of quark. In your atoms around your nuclei, you have the electron. And discovered in the cosmic rays as a somewhat heavier electron-like particle, another one was discovered in particle accelerators. And then in between here, you have 3 different types of neutrinos, very light neutral particles, which were very much in the news about a year or so ago, unfortunately, for all the wrong reasons. So those are the particles of matter. So between these particles of matter, we distinguish 4 fundamental interactions. 2 of them are very familiar. Gravity keeps everybody's feet on the ground, even particle physicists. Electricity and magnetism, that's responsible for light, radio waves. And then inside the nucleus, there is a strong force that holds the nucleus together, and a weak one that is responsible for forms of radioactivity. And I like to think of what you see on this slide as being, in some sense, the cosmic DNA. This is what encodes all the information necessary to make all the visible stuff in the universe. There's a bunch of invisible stuff out there, which is not described by the standard model, but at least this describes all the visible stuff in the universe. Except there is one element missing. The big problem with this theory is, why do things weigh? Why do particles have mass? So we heard already about Galileo. I'm sure you're also familiar with Newton. Newton, of course, told us that weight is related to mass. I've already talked about Einstein. Einstein told us that energy is related to mass, E equals mc squared. Unfortunately, all these honorable gentlemen somehow forgot to explain where the mass comes from in the first place. And the answer to that question may have been provided by this gentleman here. This is Mr. Higgs, who was from King's College London, where I'm now affiliated. And you can see his theory on the blackboard behind him. You can also see his theory on my T-shirt. So the top line of my T-shirt describes the fundamental interactions. The second line, how these interactions work on the particles of matter. The 2 bottom lines, these are Mr. Higgs's theory. This line describes how it gives masses to particles, and this is the sort of engineering details down here. Now, according to this theory, there must exist another particle, as yet unseen. That is the one we call the Higgs boson, which in some sense has become the holy grail of particle physics. So I want to give you an analogy for thinking of the way that this idea works. So according to the ideas of Higgs and friends, there is a sort of medium filling all of space. Let's think of a snowfield. Imagine that you're over in the Mall with a ski slope. Okay? Imagine that there is this uniform, isotropic, homogeneous, infinite in extent snowfield. Perhaps you're in Siberia. Now imagine you're trying to cross this Higgs snowfield that fills the universe. Maybe you've got skis on. If you've got skis on, then you skim very quickly across the surface of that snow. You don't sink into the snow. You don't interact with that Higgs snowfield. You go very fast. That's like a particle traveling at the speed of light, maybe a photon. Alternatively, you may have snowshoes on. If you have snowshoes on, you sink into the snow. You interact with that Higgs snowfield. You go more slowly than the skier. That's like a particle with mass, an electron, maybe. And then, of course, maybe you don't have any snow equipment at all, and you try to walk across Siberia in your boots. You're going to sink very deeply into that snow field. You're going to interact very strongly with that Higgs boson, and you're going to get a large mass. Now, how do you prove this idea of this Higgs snowfield? Well, what is snow made of? Snow is made of snowflakes. In the same way, we've already heard the Q word, the quantum. There is a quantum, a smallest unit of this Higgs snowfield, and that is the Higgs boson. And what the experiments at CERN have been trying to do, what we think we did last year, was finally to observe this missing particle, the Higgs boson. Okay, so this is a computer simulation of what this Higgs boson might look like. So you have to imagine in this picture that two proton particles collided along here. They produce dozens of other particles coming out. Also the Higgs boson. You can't see the Higgs boson directly. It's neutral. It decays very, very quickly. But in this simulation, it decayed into two energetic particles coming out over here and another two over there. That's one of the key signatures of the Higgs boson that the experiments have been looking for and that we think they have now found. So this is a picture down in the 27-kilometer circumference tunnel where the Large Hadron Collider is located. So what you can actually see here, this is part of the ring of magnets going all the way around, and through those magnets there circulate thousands of billions of particles, which we try to make collide. Each of those particles has, roughly speaking, the energy of a fly. And with those collisions, we hope to understand, as I already said, where mass comes from, the nature of the dark matter that fills the universe, the nature of the plasma that filled the very early universe. So here's a view what's going on inside those magnets. So there are tubes where the particles circulate. We want the particles to go all the way around in opposite directions so that they can collide. That means that in those tubes, we have to have a very good vacuum so that they don't hit particles of gas and get obstructed as they're trying to go around. That vacuum is actually better than the vacuum on the surface of the moon. We need very powerful magnets to keep those particles going around in circles. In order to get very powerful magnets, we have to cool them down to a very low temperature. In fact, it's 1.9 degrees above the absolute zero, the lowest possible temperature. That's actually even lower than the temperature of outer space. Outer space is filled with radiation, which has a temperature 2.7 degrees above absolute zero. So we claim that particle physics is 0.8 degrees cooler than outer space. Except when we make a collision. When you collide the particles, for a very brief instant, you get a little hot spot where the temperature is perhaps 1 billion times higher than it is in the interior of the sun. Now, of course, when that happens, you get lots of particles coming out, and you try to observe those particles with large particle detector experiments. And we have 4 big ones. So over here we have the largest of them all, called Atlas, which is looking for the Higgs boson and dark matter particles. You can judge how large it is, because if you look very, very carefully, you see a person there. It's a regular-sized person, not a Lego person. And that tells you that this thing is something like 25 meters tall and almost 50 meters long. There's a rival experiment also looking for the Higgs boson and dark matter particles, and the other ones are looking for other aspects of physics that I won't go into in this particular talk. So, back in 2009, after some technical hiccups that you probably heard about, we got the thing to work, and here you see a whole bunch of very happy physicists when they saw the first collisions. They're all happy, even her. But she's the person with her finger on the red button to stop it if anything goes wrong. So she's looking at it very carefully. But nothing did go wrong. It worked very well. And as has already been mentioned, in the middle of last year, perhaps we finally saw this previously unseen particle, the Higgs boson, finally emerging. And this triggered what I can only describe as mass Higgs hysteria, at least amongst particle physicists. So let me show you some of the events that set particle physicists' blood racing. So this is an example of one event observed by the Atlas experiment. So remember in the computer simulation I said that the Higgs boson might decay into 4 energetic particles coming out as long straight lines. So here are 1, 2, 3, 4 such energetic particles. This could very well be the decay of a Higgs boson. This is another example from the rival experiment called CMS. In this particular event, they were looking for something a little bit different, where the Higgs boson might be decaying into a pair of energetic photons, particles of light. You can see one over here and one over there. So these are candidates for what we think might be the production and then the subsequent decay of this holy grail of particle physics, the Higgs boson. So on July the 4th, the 2 experiments brought their results together. They presented them in a seminar at CERN, and the strength of the signals that they were observing allowed each of them independently to claim that they had discovered a new particle. And here you see some of the newspaper headlines from around the world. This was rightly celebrated. Actually, these people were celebrating the result of a football match. At least he was celebrating, she wasn't. These are the physicists celebrating. And this is a picture that I like. On the right, you have Peter Higgs, one of the originators of this idea. Here is François Englert, another one of the originators. The original papers on this subject were written back in 1964. The discovery of this new particle was made in 2012, so a difference of 48 years. Turns out that these 2 originators of the theory had not met in all that time. They met for the first time on July the 4th, 2012, to see the discovery of what is probably their particle. So let me show you an update of the data as was shown in December at the end of last year. So along here, you see a sort of basically a flat line, little sort of statistical fluctuations, but basically 0. What that means is that there is no Higgs boson on the left, no Higgs boson on the right. But here you see a bump. There is something happening here, and that is what we believe may be the Higgs boson, finally emerging from the background of uninteresting events. So I've taken you a little bit behind the scenes. I've talked about why the Higgs boson is so important, talked a little bit about how the Higgs boson has been searched for, and something about what has actually been found. I'd like to close just by saying a couple of things. One is that this Higgs boson is a big deal. Let me just give you an example. If there was no Higgs boson, there would be no atoms. There would be no atoms because electrons would have no mass. Electrons would escape from nuclei at the speed of light. There's no way for holding atoms together. Moreover, the weak interactions which are responsible for radioactivity would not be weak. They would be as strong as, for example, electricity. That means that everything would glow in the dark, and life as we know it would be totally impossible. So the existence of this Higgs boson is a big deal. Finally, I would just like to add with one final comment. This discovery is not something that belongs to some laboratory in Geneva in Switzerland. These experiments have been carried out by groups of thousands of physicists from dozens of countries around the world. And here I show you a little picture of where all these physicists have come from, including quite a number of countries in this region, although I must point out, not from the UAE. Thank you.